As we have seen earlier that ethylenic protons, aldehydic protons and benzylic protons, they are highly de-shielded protons, whereas acetylenic protons are shielded protons. The data cannot be explained just by taking into consideration the electronegativity effect. This can be explained on the basis of anisotropic effect. Anisotropic effect can be explained by taking the example of ethylene molecule. When ethylene molecule is placed under the influence of external magnetic field, then the molecule automatically is so oriented that the pi electrons become perpendicular to the external magnetic field. That is, the molecular axis of ethylene molecule is perpendicular to the external magnetic field. Now in ethylene molecule there are pi electrons, and electrons are negatively charged. They are also spinning. So in presence of external magnetic field, due to the spinning of pi electron, there will be a magnetic field generated by the circulation of pi electron, and this magnetic field is known as the secondary magnetic field. This secondary magnetic field is not even throughout the space. In some area it is parallel to the external magnetic field BO, and this area is known as the paramagnetic area. And in other area the secondary magnetic field is opposite to the external magnetic field BO, and this area is known as the diamagnetic area. In paramagnetic area, the effective magnetic field is more than the applied one, because the secondary magnetic field is add up to the external magnetic field which is applied, and in case of diamagnetic area the effective magnetic field is less than the applied one, because the secondary magnetic field cuts down the strength of external magnetic field. So the conclusion is that in paramagnetic area BO effective is more than the BO applied. So the protons, if they are present in paramagnetic area, they will be de-shielded, and in case of diamagnetic area the effective magnetic field is less than the applied magnetic field, and if protons are present in diamagnetic area, then the protons will be shielded protons. Now the question is, which area is paramagnetic and which area is diamagnetic? So the secondary magnetic field which is generated, it forms a cone with respect to axis, central axis. Area under the cone represents the paramagnetic area, and area out of the cone, that is the 36-degree angle, represents the diamagnetic area. So if the protons are present in paramagnetic area, then protons are de-shielded, and if the protons are present out of the cone, then the protons are shielded. So we can explain why ethylenic protons are highly de-shielded, because they are present in the paramagnetic area where the BO effective is more than the BO applied. Let us see some examples to explain the anisotropic effect. Now in this compound, that is the 4-methyl 1,3,5 heptatriene, there is a methyl group, and the delta value for this signal of methyl group is 1.9 delta. We know that the methyl proton shows the absorption at 0.9 in case of alkenes. But here, since it is an unsaturated compound, it is bonded to sp2 hybrid carbon atom, then therefore it is a delta value is 1.95, and it is because of the methyl protons are present in the paramagnetic area which is generated by the circulation of pi electron. That's why there is a chemical shift from 0.9 delta to 1.95 delta. Another example is of alpha-pinene. In alpha-pinene, there are 3 methyl groups, 1 methyl group and 2 JAM dimethyl groups. This methyl group is in the plane of double bond. Therefore, this shows the absorption of 1.63 and it is very close to the delta value in this compound 4-methyl-1,3,5 heptatriene. But the two gem dimethyl groups here, one methyl group shows a signal at delta 0.85 and another methyl group shows the signal at delta 1.27. Why there is a difference in the absorption position? One is de-shielded with respect to other methyl proton. If we see the structure carefully, then we will find that the methyl group this falls at the diamagnetic area generated by the circulation of pi electrons here. So the methyl proton, which shows a signal at 0.85, is slightly shielded proton, whereas the methyl protons, which shows a signal at 1.27 delta, they are away from the diamagnetic area. Therefore, they are relatively de-shielded protons. With the help of anisotropic effect, we can explain why acetylenic protons are highly shielded protons. So when acetylene is placed under the influence of external magnetic field, the molecule automatically so oriented that the molecular axis become parallel to the external magnetic field. And here also by the circulation of pi electron, a secondary magnetic field is generated, and somewhere it is paramagnetic and somewhere it is diamagnetic. So the protons are present in the diamagnetic area. Therefore, the acetylenic protons are highly shielded protons. And in diamagnetic area, as we know, that the BO effective is less than the BO applied. This concept can be used to distinguish between terminal alkynes and the internal alkynes. In terminal alkynes, there is a proton which is bonded to sp hybrid carbon atom. So this proton will be highly shielded proton. This proton, terminal alkynes, this proton will be highly shielded proton. And in case of internal alkyne, there is no proton bonded directly to the sp hybrid carbon atom. Therefore, this signal will be absent in case of internal alkyne. So by the application of NMR, we can distinguish between terminal alkyne and the internal alkyne. The question can be asked why aldehydic protons are highly de-shielded protons. The signal because of the aldehydic proton is seen at delta 9 to 10. These protons are highly de-shielded because of the anisotropic effect. There is a double bond between carbon and oxygen, that is a carbonyl group here, and by the circulation of these pi electron, again a secondary magnetic field is generated. Somewhere it is paramagnetic, somewhere it is diamagnetic, and since the aldehydic protons falls in the paramagnetic area, where the effective magnetic field is greater than the applied magnetic field, therefore aldehydic protons are highly de-shielded protons. So here also, which area is paramagnetic and which area is diamagnetic, we can see the cone here. And area under the cone represents the paramagnetic area and the area outside the cone represents the diamagnetic area. And this is the axis passing through oxygen, and 43 angle is the diamagnetic area, and area under the cone is paramagnetic area, and aldehydic protons falls in the paramagnetic area. Therefore, aldehydic protons are highly de-shielded protons. So if we see a signal here between 9 to 10 delta, and from IR if we confirm there is a carbonyl group present, then by looking at this signal of aldehydic proton, we can conclude that the aldehyde is present. Now look at the NMR spectrum of acetone. There are two methyl groups and All the 6 protons are equivalent proton, therefore we see only one signal, and because of the anisotropic effect of carbonyl groups, methyl protons are d-shielded protons, and the signal is seen at delta 2.3 in place of 0.9 delta. So this indicates that the protons in case of acetone, methyl protons in case of acetone, they are the d-shielded protons. This is the NMR spectrum of acetaldehyde. There are two signals. One signal is because of 3 equivalent methyl protons here, which is seen at 2.3 delta, and one signal because of aldehydic proton, and it is out of the scale here. So this proton, from the NMR data, it is very clear that the aromatic protons are more d-shielded as compared to ethylenic protons. The question is, why aromatic protons are more d-shielded than ethylenic protons? The answer lies in the structure of benzene or aromatic compound. In aromatic compound, we know that the pi electrons are cyclically delocalized. So when benzene or any other aromatic compound is placed under the influence of external magnetic field, then by the circulation of pi electrons, a strong ring current is generated. And because of this ring current, very strong magnetic field is generated, and this magnetic field is not even throughout the space. At the periphery, it is paramagnetic. Paramagnetic means the effective magnetic field in this area will be more than the applied magnetic field. Here, the secondary magnetic field adds up to the external magnetic field. But in the center, this secondary magnetic field is diamagnetic. That is, it cuts down the strength of external magnetic field. So this is the diamagnetic area. And in benzene ring, 6 protons are present at the periphery, that is, they are present in the paramagnetic area. Therefore, 6 protons of benzene are highly d-shielded protons, and they show the signal between delta 7 to 8. So this is a very strong tool to decide whether the compound is aromatic or it is non-aromatic. This is the NMR spectrum of benzene. And this NMR spectrum of benzene shows only one signal, and that too at delta value 7.2. This shows the aromatic compound. Only one signal is present. It means all the 6 protons of benzene are equivalent protons. Now, if we study the chemistry of benzene, then we know by nitration we get only one isomeric nitrobenzene. On chlorination, we get only one chlorobenzene. So chemical reaction, electrophilic substitution reaction also shows that all the 6 protons are equivalent here. And similarly, only one signal is obtained in the case of benzene. It further proves that all the 6 protons in benzene are equivalent protons, and they are highly d-shielded protons. This is the NMR spectrum of toluene. In toluene, there are 2 different types of protons, non-equivalent protons, 3 equivalent protons of methyl group, and 5 equivalent protons of benzene, benzylic protons. So one signal is seen close to 2.3 delta, and another signal is seen near about 7.2 delta. And this is the 5 equivalent benzylic protons. Here, the methyl group is more d-shielded as compared to the methyl protons present in the acyclic conjugated system. They show the absorption at 1.95 delta. Why the methyl protons in case of toluene are more d-shielded as compared to methyl protons of acyclic conjugated system? Because of the strong ring current which is generated by the circulation of pi electron, the de-shielding of methyl protons in case of toluene is more as compared to the methyl protons present in acyclic conjugated system. If the NMR spectrum of compound is recorded on a very sensitive NMR instrument, say 600 MHz NMR instrument or 700 MHz NMR instrument, then we can get different signals for ortho, meta and para protons in monosubstituted benzene compounds. For example, here the NMR spectrum of phenol shows a signal at delta 6.1 because of the orthoprotons, another signal at 6.9 because of the paraprotons, and a third signal at delta 7.1 because of the metaprotons. So why there are three different frequencies are recorded for ortho, meta and paraprotons in case of phenol? The answer lies in the resonating structures of phenol. We know that by plus M effect, lone pair of electron which is present on oxygen gets delocalized with 6 pi electrons of benzene, and because of this delocalization we can write these three canonical structures for phenol. In these three canonical structures we see electron density is increased at both the ortho positions and at the para position as compared to the electron density at meta position. Therefore, the protons present on ortho and the para position get shielded because electron density is more at the ortho and the para position, and the meta protons are relatively de-shielded. Now, this also explains that hydroxyl group is ortho and para directing. We know by the presence of OH, benzene ring is activated towards the electrophilic substitution reactions, and the incoming electrophile goes to the ortho and the para position. Why it goes to the ortho and para position? Because electron density is more at ortho and the para position as compared to the meta position. And this is also very much indicated in NMR spectrum also, because ortho and the para protons are shielded as compared to the meta proton, where the electron density is comparatively less. The resonance frequency of ortho, meta, para protons in disubstituted or polysubstituted benzene compounds can be determined by adding the increment due to the substituent present in benzene ring. For example, here we have taken meta-diacetyl benzene. In meta-diacetyl benzene, there are two acetyl groups which are present meta to each other. From the table, we can see the increment due to acetyl group. These tables are given in every book. So increment due to the acetyl group at orthoproton is plus 0.63, and increment due to the acetyl group at meta and the paraproton is plus 0.28. Now here we will see how we can determine the resonance frequency of different protons, ortho, meta and paraprotons. C2 protons, here there are two acetyl groups with respect to C2 protons. It means C2 protons are ortho to acetyl groups. So the resonance frequency of this will be the base value of benzene, that is the 7.2, plus the increment due to the acetyl group at orthoproton. For one orthoproton, the value is 0.63. Since at C2 there are two acetyl groups ortho to C2 protons. Therefore, the figure will be doubled, that is 0.63 multiplied by 2 is equal to 1.26. So when 1.26 is added to 7.2, it becomes 8.46. That the signal because of C2 protons will be seen at 8.46. Now look at the protons C4 and C6. C4 protons and C6 protons are equivalent protons. At C4 proton, this acetal group is ortho, whereas acetal group present at carbon number 1 is para with respect to C4 protons. Similarly here at C6 protons, acetal group present on carbon 1, that is the C1 protons, is ortho, and the acetal group present on the third carbon is, here it is para. So C4 proton and C6 protons will observe the ortho increment as well as the para increment. So ortho increment is 0.63 and the para increment is 0.28. If we add 0.63 and 0.28, it becomes 0.91. So by adding 0.91 to base value of benzene, that is 7.2, the resonance frequency of C4 proton and C6 proton will be 8.11. Now we can calculate the resonance frequency of C5 protons also. Acetal groups are meta with respect to C5 protons, and for the meta increment is 0.28. So at C5 it will observe two acetal groups effect because they are meta to each other. So the increment will be double of 0.28, that is 0.56. So this 0.56 is added to the base value of benzene, 7.2 delta. So the meta protons will show the absorption at delta 7.86. So in this manner, if we see the increment value of different substituents from the table and we can add up to the base value of benzene, so we can determine the resonance frequency of ortho, meta and para protons in disubstituted or polysubstituted benzene compounds. Now take the example of nitrobenzene. From the chemical reactions of nitrobenzene, we know that the incoming electrophile goes to the meta position when the substitution is carried out. Presence of nitro group in benzene ring deactivates the ring towards a further electrophilic substitution reaction. It is because when nitro group is present, it withdraws the electron towards itself and electron density is decreased at the ortho position and at the para position. So these two positions, ortho and the para, becomes electron deficit. Therefore, the incoming electrophile goes to the meta position. If we discuss this in terms of NMR, then we see that at the ortho position and at the para position, electron density is decreased. Therefore, the proton should be de-shielded. And from the data, it is very clear that the ortho proton shows the absorption at 8.2 delta and para proton shows the absorption at 7.7 delta value. Whereas meta protons, where the electron density is relatively better than ortho and the para protons, is slightly shielded protons and the signal is seen at 7.5 delta value. So here we can correlate the signal from ortho-meta paraproton, that is the resonance frequency of ortho, meta and paraprotons with the reactivity of nitrobenzene. This is a very interesting example. We know that pyrene is a polycyclic aromatic hydrocarbon. This is pyrene, polycyclic aromatic hydrocarbon, and its derivative is dihydrodimethylpyrene. The two methyl groups here are added. Now, when NMR spectra of dihydrodimethylpyrene is taken out, in this NMR spectrum, the signal from the methyl proton is seen at the delta minus 4.2. Delta minus 4.2 means the signal is seen above TMS. That is, the resonance frequency of methyl protons here is lower than the precessional frequency of tetramethylsilane protons. Why it is so? Whether this compound is aromatic or it is non-aromatic. So in this compound you see there are peripheral pi electrons. By the circulation of these peripheral pi electrons, they are rotating in a circle. They are cyclically delocalized pi electrons. So by cyclically delocalized pi electrons, a strong ring current is generated. And we know that as in benzene, that somewhere it is paramagnetic and in the center it is diamagnetic. So similarly here, a ring current is generated. At the periphery it is paramagnetic and in the center it is diamagnetic. Since methyl group falls in the diamagnetic area, therefore these methyl protons are highly shielded protons, and therefore the signal is seen at delta minus 4.2. So it is an example of a non-benzenoid ring system. In 18-aniline, there are 6 inner protons and 12 peripheral protons. The peripheral proton shows a signal at delta 8.9, whereas the inner 6 protons shows a signal at delta minus 1.8. That is, here the frequency of inner protons is less than the TMS protons. Why it is so? Again here, this 18-aniline is aromatic compound. By the circulation of peripheral pi electrons, they are cyclically delocalized and a ring current is generated. And peripheral protons are present in the paramagnetic area. Therefore, like other aromatic protons, they are de-shielded protons. Whereas the inner 6 protons falls in the diamagnetic area where the effective magnetic field is less than the applied magnetic field. Therefore, these protons are highly shielded proton and the signal is seen at delta minus 1.8. If this happens only when the temperature is very, very low, the shape of the spectrum changes with change in temperature. This is a very interesting example, cyclohexane. Cyclohexane, if we consider it's a planar structure, then the 12 protons will be equivalent proton. But we know cyclohexane is present in the chair form, not in the plane. It is a puckered structure, it is not a planar structure. So when it forms a chair structure, then the protons are axial and equatorial protons. 6 protons are axial and 6 protons are equatorial protons. But at room temperature, this chair flips to the another chair. So all the axial bonds become equatorial and equatorial protons become the axial protons. So at room temperature, we cannot distinguish between axial proton and the equatorial protons. But at a very, very low temperature, NMR is a tool by which we can distinguish between axial protons and equatorial protons. Equatorial protons are slightly de-shielded because they are present in a cone which is generated by the gamma, beta, sigma electrons. Here it is not the pi electron, it is the sigma electrons of the bond beta and gamma, and by this a secondary magnetic field is generated. It is paramagnetic somewhere, it is dimagnetic in some area. So equatorial protons falls in the paramagnetic area. Therefore, the equatorial protons are de-shielded. When protons are present on nitrogen, oxygen or sulfur, they are de-shielded. Why they are de-shielded? Because of the electronegativity of oxygen, nitrogen and sulfur. So when proton is bonded to nitrogen, the signal is seen somewhere 2 to 3.5 delta, and when hydroxyl proton is seen somewhere between 2 to 5 delta. Now these protons show hydrogen bonding also, and because of the hydrogen bonding, if it is a intermolecular hydrogen bonding, then it is temperature dependent and the concentration dependent. And these protons can be exchanged by deuterium also. We know that hydroxyl protons are de-shielded protons, and hydroxyl protons show the hydrogen bonding. Hydrogen bonding may be intermolecular or intramolecular hydrogen bonding. Here is the case of intermolecular hydrogen bonding in alcohol, and the delta value is concentration dependent and temperature dependent. In case of intramolecular hydrogen, which is shown by enol of beta diketone and a carboxylic acid dimer, here the delta value will not change with the change in concentration and the temperature. This is the NMR spectrum of methyl alcohol, and it shows two signals, one because of the methyl protons and one because of the hydroxyl proton, and the signal from the hydroxyl proton is seen at 4.5 delta, whereas the signal from the methyl proton is seen at 3.4 delta. Phenolic proton is more de-shielded as compared to hydroxyl proton because of the resonating structures of phenol, and the signal is seen between delta 4 to 7.5. Here this is an ester, and in salicylates this hydroxyl proton is highly de-shielded. The signal is seen at delta 10 because of the de-shielding effect of this carbonyl. So this delta value is approximately 10 delta, and in case of salicylates this is intramolecular hydrogen bonding. Therefore, it will be temperature and the concentration independent. This is a very interesting example, orthohydroxyacetophenone and parahydroxyacetophenone. So by NMR spectrum, we can distinguish between orthohydroxyacetophenone and parahydroxyacetophenone. The difference between the two compounds is that orthohydroxyacetophenone shows the intramolecular hydrogen bonding, whereas the parahydroxyacetophenone shows the intermolecular hydrogen bonding. So as we have seen that intermolecular hydrogen bonding will be concentration dependent. So at 1 m concentration, the signal of hydroxyl proton is seen at delta 6.3, whereas at infinite dilution, the signal is at 5.6 delta value. That is, with the change in concentration, the position of signal is also changing. Whereas in case of orthohydroxyacetophenone, there is intramolecular hydrogen bonding, and because of the strong anisotropic effect of carbonyl group, it is the delta value of the hydroxyl proton is at delta 12 to 10, and it is not concentration dependent. This is the NMR spectrum of acetic acid CH3 C double bond OOH. In acetic acid, there will be two signals, one because of the methyl protons and one because of the hydroxyl proton. So there is a signal at 2.0 delta. This is because of the methyl protons, and The hydroxyl protons are highly de-shielded. The signal is seen off the scale. Off the scale term is used when the signal is above 10 delta value. Why it is highly de-shielded? Because the acids are present in the dimeric form. So here the signal is 2.5 ppm offset. It means the signal is seen at about 12.5 delta value. By looking at the NMR spectrum, we can predict that it is the spectrum of methyl esters of aliphatic acid. How it can be done? How it can be interpreted? Because in the methyl esters, this methyl protons which are bonded to this oxygen, so they will show the signal at 3.6. So here the value of R can be anything. It can be a methyl acetate, or R can be butyl group, or it can be propyl group, pentyl group, any R can be any alkyl group. But this methyl will show the absorption at delta 3.6. So from the NMR spectrum, if there is a signal at delta 3.6, so we can say that it may be a methyl ester of aliphatic acid along with other data which are supported by IR and mass values also. Protons present on nitrogen are also de-shielded protons because of the electronegativity of nitrogen. In case of amines, the signal is seen between delta 0.5 to 3. Amines also show the hydrogen bonding here, and intermolecular hydrogen bonding is concentration dependent as in case of hydroxyl protons. That is, aniline shows the signal somewhere between 3 to 5 delta, and in case of amides, the signal is seen at delta 8.5 to 5 delta value. This is a very interesting example, N,N-dimethyl formamide. N,N-dimethyl formamide is present in two resonating structures. In one, there is a single bond between carbon and nitrogen, and by the delocalization of electron, in the second structure, resonating structure, there is a double bond between carbon and nitrogen. Because of the double bond character here between carbon and nitrogen, the rotation at carbon-nitrogen is restricted. So at room temperature, it shows two signals for the methyl groups. Now the two methyl groups are non-equivalent because one methyl group is present on the side where oxygen is present, and another methyl group is 180 degrees away from the negatively charged oxygen. So methyl proton shows one signal at 2.88 delta value, and other methyl proton shows a signal at delta 2.97, and it is because of the restricted rotation at carbon-nitrogen double bond. Proton present on sulfur is also de-shielded, as we can see in case of thiols. In case of ethane thiol, the signal is seen at delta 1.4, and in thiophenol, the proton signal is seen at 3.5 delta value.